Okay, sir. So, hello, good day, everyone. This is Sunil Kumar Pradhan. In this session, we'll discuss about some problems and associated solutions with electronic materials and devices. So, let's consider this question number one, as shown in the figure one. That it says that that is a unit cell and unit cell of copper crystal. So, if you can see, this is a copper which is actually, if you can see, this is a face-centered cubic. Face-centered cubic means that means the atoms are arranged at the corners of the cube, and along with atoms are also situated in each face. That means in a cube there are six faces are there, so atoms are arranged in the six faces. And if you can see here, this is one unit cell. So in this unit cell, if r is the radius of copper atom and the radius of copper atom is 0.128 nanometer, then you have to find out what is the lattice parameter, and second is the atomic packing factor. Okay. So then, so the lattice parameter is calculated in FCC structure as 2 root 2 r. If r is the radius, then 2 root 2 r is the lattice parameter. So r is 0.128 nanometer here. So your lattice parameter will be 0.3628 nanometer. Okay. And how to find atomic packing factor? Packing factor is calculated as volume of atoms divided by volume of the cube. So volume of the atoms, as you know, if r is the radius of the atom, so it will be 4 by 3 pi r cube, and volume of the cube will be 16 root 2 r cube. So it is coming to be 0.74, and that means at 74%. Okay. So this is question number one. Now let's consider question number two, that find the magnitude of Hall voltage in an N-type germanium semiconductor bar used in figure two. Okay, so in figure two, if you can see, this is a to find out what is the Hall voltage here. That means if you can see, this is in x direction the current I. This, if you can, let's say y direction electric field and z direction is the magnetic field. Okay, and d is the, you can say, the thickness, that is 3 millimeter. And if you can see here, as per the questions, the majority carrier concentration, that means your donor atoms is Nd is 10 to the power 10 to the power 17 per centimeter cube. And electron mobility is also given. Electron mobility for germanium is 3800 centimeter square per volt second. Now there are some data are given as per the questions, that you have to that the magnetic field is 0.1 Weber per meter square. D is 3 millimeter and electric field is 5 volt per centimeter. Okay, so what will happen to the Hall voltage here? Second question is, what happens to the Hall voltage if an ideal p-type germanium, previously it is n-type germanium, what happens to the Hall voltage if identical p-type germanium bar having majority carrier concentration, the same majority carrier, that means in that cases 10 to the power 17 per centimeter cube used as in the as shown in the figure and as per the question number one. Okay, so what will be the Hall voltage? So how can we find out? So if E the electric field, then the force experienced by the charged particle is Q into E. The Q the charge, E the electric field, and the force due to magnetic field will be QBB, where V the velocity, B the magnetic field, Q the electric charge. So here Q will be cancelled out, so it will be E is equal to VB. So E the electric field and V the dip velocity and B the magnetic field. Hall voltage, we know it will be electric field into distance. Okay, because you know electric field is voltage per distance, so definitely Hall voltage will be E into D. Now E, as per this equation, will be V into B, so we can substitute here, so it will be VD. So but V is equal to, you know, that V the drift velocity, mu the mobility, and E the electric field. V is equal to mu E. So that that relation we can keep it here. So what will be VH? V will be mu E, so mu E D. Okay. So if you put all the values here, so B will be 0.1, Weber per meter square. Mobility is 3800 into 10 to the power minus 4, and electric field is already given, and D is already given. So if you put all the value, it will be coming as 57 millivolt. Okay. And the second question is here, what happens to the Hall voltage if identical beta German is used, and the acceptor concentration is 10 to 17 centimeter cube. So Hall voltage will be remain same, but it changes its polarity. Okay, so in this case, the Hall voltage retains the same value, that is 57 millivolt, but it changes its polarity. So this is the solution of this question. Then we move to second question, that an n-type silicon wafer has been doped uniformly with 10 to the power 16 arsenic atoms per centimeter cube. That means it is a pentavalent impurity, and you have to find out what actually the position of Fermi energy with respect to the Fermi energy in intrinsic silicon. Okay. Next question is, if the above n-type silicon sample is further doped with 2 to the power 17 boron atoms per centimeter cube, then what position of Fermi energy with respect to Fermi energy of intrinsic silicon? Okay, assume that your room temperature is 300 Kelvin, and KT, where K is the Boltzmann constant, T is the absolute 0 degree temperature, so it will be 0.0259 electron volt. Okay. So how can we find out this solution? Now arsenic gives the n-type doping, so that means your donor atoms is 10 to the 16 per centimeter cube as shown in this question. Now this donor atom is very greater than your intrinsic carrier concentration. That means 1 into 10 to the 10 per centimeter cube. Okay. Now we have n is equal to nd, that is 10 to the 16 per centimeter cube. So what will be for intrinsic silicon? This, if Ni is the intrinsic carrier concentration, if Nc is the density of states at conduction band H, then it will be e to the power minus Ec minus EFi divided by Kt. Okay. Then as for doped silicon, this electron concentration will be Nc, that is your density of states at the conduction band H, into e to the power minus Ec minus EFn divided by Kt, that nothing but your equal to your donor atom concentration. Because for doped silicon, for n-type semiconductor, the donor atoms concentration will be equal to your electron concentration. Okay. What is EFi, EFn? EFi, EFn are the Fermi energy in intrinsic and n-type silicon. Okay. Now, if you can divide these two equations, it will be Nd divided by Ni. It will be e to the power minus EFn minus EFi divided by Kt. So if you can find out EFn minus EFi, so Kt ln Nd by Ni, if you can put the values, because it's given in the question, so it is going to be 0.36 electron. So this is the solution of first question. That means what is the position of Fermi energy with respect to Fermi energy of intrinsic silicon? So that is 0.36 electron volt. Okay. The next question is that if the above n-type silicon is further doped with 2 to the 2 into 10 to 17 boron atoms per centimeter cube, then what is the position of Fermi energy? Fermi energy, that is intrinsic Fermi energy of an intrinsic silicon. So here the wafer is doped with boron atom. That means the acceptor concentration is given 2 into 10 to the 17. If you can see, to the 2 into 10 to the 17 boron atoms. So your that equal to, which is very greater than your donor atoms, 10 to the 16 per centimeter cube. Now the semiconductor is compensation is doped, and compensation converts the semiconductor to p-type silicon. So what is my acceptor concentration? That is Na minus Nd. 2 into 10 to the 17 minus 10 to the 16, it will be 1.9 into 10 to the 17 per centimeter cube. Now for intrinsic silicon, your intrinsic carrier concentration will be Nb e to the power minus EFi minus Eb by Kt. What is Nb? Nb is the density of states at the valence band H. Whereas for doped silicon, your whole concentration will be Nb e to the power minus EFi minus Eb divided by Kt. So that is equal to Na minus Nd, where EFi and EFe are the Fermi energy in the intrinsic and p-type silicon respectively. Now if we can divide these two equations, P whole concentration divided by intrinsic carrier concentration, then it will be e to the power minus EFe minus EFi divided by Kt. So your EFE minus EFI will be minus KT ln P by Ni. So it is coming to be minus 0.43 electron volt. That is the solution of the second part. That is what is the position of Fermi energy with respect to the Fermi energy of intrinsic silicon. So that is minus 0.43 electron volt. Okay. So this is the solution of this question. Now, next question is find the resistivity of intrinsic silicon at room temperature. Taken into consideration, the intrinsic carrier concentration is 1.5 into 10 to the 10 electron per centimeter cube. Now, the electron mobility is also given, that is 1300 centimeters per volt second. Hole mobility is given 500 centimeters per volt second. Now, how to solve these questions? Now, for an intrinsic silicon at 300 degree Kelvin, what is the intrinsic carrier concentration? Already given 1.5 into the 10 electrons per centimeter cube. The mobility of electron is 1300 centimeters per volt second, and mobility of hole is 500 centimeters per volt second. Now, what is my conductivity here? That will be your intrinsic carrier concentration uh, with multiplied by summation of mobility of electron concentration plus mobility of hole concentration. So if you can put this value, you can find the conductivity. That is 4.32 into 10 to the power minus 6 ohm centimeter inverse, or Siemens per centimeter, you can say. So what is my resistivity? Resistivity is nothing but reciprocal for conductivity. So it is coming to be 2,31,000 ohm centimeter. So 231,000 ohm centimeter. That is the resistivity. So this is the solution of this this question. We have to take care of the unit here, and so it is expressed in ohm centimeter. Okay. So this is the solution of this question. The next question is that consider a semiconductor with the following parameters. What are the parameters given? Electronic charge, 1.6 into 10 to the power minus 19 coulomb. Electron mobility is given 1200 centimeters square per volt second. Thermal voltage KT by Q is 26 millivolt. Electron concentration is given 2 into 10 to the 15 centimeter to the power minus 3. Electric field is 400 volt per centimeter. Special gradient of electron concentration is 2 into 10 to the 20 centimeter to the power minus 3 per centimeter. You can say 2 into 10 to the 20 per centimeter to the minus 4. So what is the drift current density and diffusion current density of electrons in the semiconductor? That is the question here. How to solve this question? So drift current density is nothing but your conductivity into electric field. So conductivity is nothing but your charge into electron concentration with the mobility of electron concentration into electric field. So all the values are given. So if you put the values, it come to be 1.536 ampere per meter square. And what is the diffusion current density? Is Q dN dN by dx. What is dN? Is the diffusion constant for electron, and del N by del X is the electron concentration. Okay, electron concentration gradient, that is del N by del X. Now dN is nothing but mu n KT by Q. Okay, so you can put all the values here. So dN will coming to be 31.2 centimeters per second. So diffusion current density will be 1.6 into 10 to minus 19, 31.2 into 2 into 10 to 20. So it is coming to be 998.4 ampere per centimeter square, or it will be 9.984 ampere per meter square. Okay. So this is the solution of this question. I hope you understood the concept here. If you like the content, please like and subscribe so that it will help me to come with new content in near future. Okay, so thank you everyone, thank you so much.